All right. Hello, good morning, everybody. Welcome to those in Marcus and those joining the live stream. I hope you guys had a nice break. So just a couple quick reminders. So our chapter 3 quiz is on Monday. So you'll have to find a 1-hour time period to submit that on Moodle, just as we did with the previous ones. Same sort of setup, 10 questions, multiple choice, similar to mini quizzes. There is a review tonight on derivative techniques from 5 to 6, and again on Monday from 4 to 5. So definitely feel free to check that out if you think that would be beneficial. So today we are going to be finishing up our techniques. We're going to cover the product rule and the quotient rule. So we will probably not get through all of the examples of both. Usually we start this sort of at the end of the chain rule, but we'll make sure that we do plenty of examples so that you understand the techniques and how these work. So I'm going to go ahead and switch over to the .cam. Okay, so we're going to start off by talking about the product rule. So the product rule, first let's talk about what is a product. A product is when you multiply two things together. So in earlier derivatives that we looked at, we talked about what happens with addition and subtraction. We said if things are separated by addition and subtraction, we can go ahead and take the derivative of each piece and put them back together with the same addition or subtraction sign. We said we can't do that with multiplication and division, and that we would have special ways to address that. So here we are. So the product rule is looking at what do we do when we have two functions multiplied together, f of x times g of x. So we come up with a formula, and that formula comes from doing limits of different things multiplied together, doing some fancy algebra, and figuring out that there again is a pattern. So we're not going to go through the theory of that, but it does again come from doing the limits, which is what we were doing back in chapter 2. We were doing a lot of that, getting really close to things to approximate and see what happens. If you do that enough, you find patterns, and from that we get the formula for the product rule. So what does this formula say? This formula says if you have two functions multiplied together, so f of x times g of x, and you want to take the derivative, that the derivative is going to be the derivative of the first function times the original second, plus the first function times the derivative of the second function. So we have this formula that we have to apply here. And so when we do it, how do we figure out what all of these pieces are? So we have these things multiplied together, but notice this piece is f prime of x. It's the derivative of this function f. So what we're going to want to do is separate our two functions that are being multiplied together and find their respective derivatives so that we can plug everything into this formula. So our plan here is we're going to do one together very, very carefully with all the steps laid out, and then we'll do some practice where you get to try some as we go along. Okay, so we're going to start with this example of x squared times e to the x. Okay, so the first and most important part of this is recognizing that we have to do a product rule. We recognize that there's two functions multiplied together, and it's not as easy as you may think. Obviously, today we're going to be looking at different product rules, but in general, if you are just given a function and told to find the derivative, you have to first determine which rule you are going to be using. Is it a chain rule? Is it a product rule? Is it the quotient rule that we'll learn later today? Is it a basic derivative? So you're looking at the structure of what you have. And so here I have two things multiplied together, and I see that I can separate them by drawing a line between them. That's one sort of small trick you can do if you're thinking it could be a chain rule, but it could be a product rule. With a chain rule, you can't separate it with a line, okay? But with a product rule, you can separate the two functions. So once you've determined that you're using the product rule, we are going to pick one of our functions to be f and one of them to be g. Because this involves things like multiplication and addition, it doesn't actually matter which of the two functions is your f and which one is g, because you'll end up with the same answer either way. However, the convention in math is to pick the first function you see between the two to be your F, and the second one to be your G. So once we've identified that we're doing a product rule, we're going to do some side work where we say, okay, the first function being multiplied, we're going to call F. The second function we see multiplied is going to be our G. Okay, so we separate those out, and then on the side, we are going to find the derivatives of each of these individual functions. And hopefully, these derivatives are not too terrible. So right here, these ones are basic derivatives. So these come from our basic rules. And again, basic doesn't mean easy, it means foundational. We will look at an example later where they're not as easy, but we're going to start with some straightforward ones. So when we take the derivative of x squared, we're using a power rule. The derivative here is 2x. When we take the derivative of e to the x, we're using the exponential rule for e to the x. And the derivative of e to the x is e to the x. Okay, so once we have those pieces, these are the 4 pieces we need to plug in to get our final answer. So here we were looking for y. So we'll say y prime, the derivative. It's going to be f prime times g. So here our f prime is 2x times our g, which is e to the x, plus f of x times g prime of x. So f of x times g prime of x is x squared times e to the x. So the derivative of x squared times e to the x is 2x times e to the x plus x squared times e to the x. Now, this is completely right mathematically, and if you were doing this on Wiley, you can enter it just like this, and it'll be correct. I do want to point out that we could factor this, and the reason I'm going to point that out is because when we move into chapter 4 next week, we'll be doing a lot more factoring of derivatives, so I just want to give you a heads up on starting that when we have some examples that are not too tricky to factor. So if we wanted to factor this, we would look for common terms. So I want you to notice that both of these have an e to the x term, so I can pull out an e to the x. And then both terms also have a factor of x to some power, okay? So when I factor this, I want to pull out the smallest power of x that I see. So I have x to the first and x to the second. So I'm going to pull out an x to the first and an e to the x. So when I factor those out, I ask what's left from the first term. What's left is a 2. What's left from the second term? Well, I only pulled out one of the x's, so there's an x left. Okay, so that's what it would look like factored. These are equivalent mathematically, so one is not more correct than the other one. The reason we might want to factor is if we are using the derivative as a first step in a multi-step process, we're going to ask questions in chapter 4 like, when does this equal 0? And then we're going to need to factor to solve for things. Okay, so for right now, this is totally fine when we're just taking the derivative, but just know that it can be factored if you needed it to. Okay, so this is what the process looks like for the product rule. So I want you to try this. So you're going to try this on the natural log of x times e to the 6x. I do want to remind you that when you take the derivative of something like e to the 6x, that 6 is going to come out to multiply in front when you take the derivative. So see if you can sort of match up the process we just did with this new function. I'm going to give you about 2.5 minutes to try to get it set up. So give it a try, and then we will go through it together. about 30 more seconds. All right. So again, we know we can do a product rule. We can separate these two functions, and we see this little multiplication symbol here. So we go ahead and we set up our side work here. We pick our first function to be our f, and our second function to be our g. And now we need to find each of their respective derivatives. The derivative of ln x is 1 over x. The derivative of e to the 6x is 6e to the 6x. The 6 can be in front of the e term or multiplied after. Either is fine, they mean the same thing. Okay, so now we're going to put these together using our product rule. So we're going to do f prime times g. So we have 1 over x times e to the 6x plus f times g prime, f times g prime. So we have the natural log of x times 6e to the 6x. There's nothing I would simplify here. There's nothing really that can be simplified. We could factor out the e term. I'm not going to do that this time, but I do want to point out that for the second term, if this was on a mini quiz, we would likely pull the 6 to the front. So you might see 6 ln x times e to the 6x. Constants usually show up in the front, so those mean the same thing, right? These three terms are multiplied together, so they can show up in any order. So you can pull the 6 to the front, and it means the same thing, okay? So hopefully that went okay for our first try at a product rule here. We're going to try the next problem, which may be unsurprising to some of you, is a find the equation of the tangent line problem. Okay. So, as we sort of go through these different types of derivatives, we're always interested in finding the equation of the tangent line. It's an application that helps us sort of understand what's happening in the background. So we're going to go ahead and do it with a product rule. So just as a reminder, in order to find the equation of the tangent line, we need a point and we need a slope. To get the point, we're plugging in our x value into the function to get the corresponding y value. And to get the slope, we're plugging our x value into the derivative. So that's where the product rule comes in, is when we find the derivative of the function so that we can find the slope for the equation of our tangent line. So I'm just going to rewrite the product rule down here just as a reminder. And then I'm going to give you about 2.5 minutes to try this out. So you can go ahead and get started. I'm just going to rewrite the product rule so that you have it for reference. And then we will go through it together. Okay, take about 30 more seconds. Okay. So again, we're going to need a point, we're going to need a slope. So let's go ahead and find our point first. If we plug a 0, because we have x equals 0, into the original function, we'll get the point that is shared between the function and the tangent line. So cosine of 0 is 1. E to the 0 is 1. So we have 1 times 1, which is 1. So when x equals 0, y equals 1. And our shared point is 0, 1. Okay, so now we need to find the derivative of our function so that we can find the slope of our tangent line. Okay, so in order to find the derivative, we look at our function here and we see that we have two functions multiplied together. So we think product rule. Okay, so we take our first function, and that's our f. And our second function is our g. You'll notice I'm being a little less formal now. Instead of writing f of x, I'm just writing f. It's just a matter of notation. Either is fine. So the derivative, f prime, derivative of cosine is negative sine. And the derivative of e to the x, we said, was e to the x. Okay, so now we have all the pieces. We want to put them together in order to find the derivative of our function. So we're going to do f prime times g. So we have negative sine x times g. Oops, I literally wrote g, times e to the x, plus f of x times g prime of x. So we have cosine x times g prime of x, which is e to the x. So we have our derivative, but we really want to know what's happening at x equals 0. So we still have to plug a 0 into our derivative. This is where some of the algebra sometimes comes back to sort of complicate things for people. Hopefully you're comfortable finding these values, but I just want to remind you that you can always double check these in your calculator if you're not sure what they are. Okay, so we have negative sine of 0 times e to the 0 plus cosine of 0 times e to the 0. And I've mentioned this before, but I'm just going to mention it again. When you're calculating values of sine or cosine, you need to make sure that your calculator is in radians. Okay, so sine of 0 is 0, and then e to the 0 is 1. So we have 0 times 1, which is 0. And then we have cosine of 0, which is 1, times e to the 0, which is also 1. So 1 times 1 is 1. So that means that the derivative at 0 equals 1. So the slope of our line for the equation of our tangent line is going to be 1. So now we have to put it all together. So we start off with y equals x plus b. So there's an invisible 1 here that represents this one. Now to find our b, this is where we bring in our point. When x equals 0, y equals 1. So we have 1 equals 0 plus b. That tells me that b equals 1. So that tells me that the final equation of my tangent line, I'll put it over here, is y equals 1x plus 1. Okay, so again, the process is the same every time we find the equation of a tangent line, but what's changing is how we take the derivative in order to find the slope. All right, so the next thing we want to try is thinking about second derivatives using the product rule. So just like other second derivatives we've tackled, we need to find the first derivative first. And then once we have the first derivative, we need to look at that as an individual function and apply appropriate derivative techniques to find the second derivative. So as we do this one, we notice that to do the first derivative, we do need to do a product rule. And I will sort of, it's not a hint, but I will recommend that you simplify the first derivative algebraically if you can before you find the second derivative. So I think that will be helpful overall. So I'm going to give you about 3 minutes to try this out. So you're going to find the first derivative using the product rule techniques we've been practicing, and then simplify the first derivative, and then apply any appropriate techniques we know to find the second derivative of this function. Okay, so try it out, take about 3 minutes, and then we'll go through it together. Okay, take about 30 more seconds. Okay. So as we start this particular problem, we are going to set up our first product rule here. So our f is going to be the natural log of x. Our g will be x to the fifth. Okay, again, it doesn't actually matter which one is your f and your g. The convention is just the first one is your f and the second is your g. Now the derivative of the natural log of x is 1 over x. The derivative of x to the fifth is 5x to the fourth. Okay, so now that we have our pieces, we're going to put them together, and we're going to go ahead and find the first derivative of this function. So we're going to do f prime times g. So we have 1 over x times x to the fifth plus f times g prime. So ln x times 5x to the fourth. And my recommendation was to try to simplify this if you can before finding the second derivative. And the simplification that can happen here is in the first term. So if you have 1 over x times x to the 5th, the x that's on the bottom here will cancel one of the x's that's in x to the 5th and simplify into x to the 4th. So we have x to the 4th plus, now the second term cannot be simplified, so we just leave that as is. Okay, and the reason we want to simplify the first term is taking the derivative of this versus this. The x to the 4th is going to be easier because that is a power rule, whereas if we leave it as 1 over x times x to the 5th, we have to set up another product rule, which we don't really want to do at this point if we don't have to. So now when we go ahead and start looking at the second derivative, we're going to go term by term. So the first term is x to the 4th. There's nothing sort of extra complicated about that that indicates that we would need to use anything other than the power rule. So we take x to the 4th, and when we take the derivative, we get 4x cubed. Okay. Now the second term, when we look at it, we have the natural log of x times 5x to the 4th. So we have two things multiplied together. And so this is where we need to recognize that we're going to need to use another product rule here. So we're going to set up the second product rule. And again, the first function, we're going to call f. The second function, we're going to call g. So g is 5x to the 4th. And then we're going to find each of their respective derivatives. The derivative of ln x is 1 over x. The derivative of 5x to the 4th is 20x cubed. So these are two different sets of side work, right? So we have to do this product rule anytime we're applying that to take a derivative. Now, I need to put this together in the product rule to find the derivative of this second term, which is going to fill in here. Whenever I do a product rule within a longer sort of function, I always put the solution in parentheses to help me remember what is connected to what. You don't have to do that, but I find it to be helpful, especially if sometimes like a negative is part of the function. You don't want to lose anything. So I'm going to use parentheses and then fill in my product rule formula here. So f prime times g, I have 1 over x times 5x to the 4th plus f times g prime, so the natural log of x times 20x cubed. Now, what would this look like if it was on a quiz or something like that? So most likely the way you would see this, you would have 4x cubed, so that first term doesn't need to be simplified at all, plus, now here, I have 1 over x times 5x to the 4th. So again, this x can cancel one of these x's. So I'm going to get 5x cubed plus, and now I have natural log of x times 20x cubed. But what I notice here is that I have a 4x cubed plus a 5x cubed, right? So I can add those together. This also has an x cubed term, but it's connected to the natural log of x. So I'm not likely to do anything with that. So this would be 9x cubed plus, and now the second term, I probably will bring the constant and the x cubed term to the front. And this is how you would see this sort of traditionally written in terms of a math solution. So I've combined the x cubed terms to get the 9x cubed. And then when you have a lot of things multiplied together, typically the constant comes first. So we would bring the 20 to the front. And then we write the functions in order of decreasing difficulty. So you're going to see x to power terms first, and then things like natural logs or e's or sines and cosines. So this is the same. It has the same 3 factors. I've just rewritten them into the order that you would likely see them presented in any sort of mathematical solution. So that's what that's going to look like once we've sort of shifted a couple things around. So that's the second derivative. That's how we might write it. Again, we have to be A little bit more careful when we get into second derivative territory. The algebra comes back a little bit more, but we can certainly do it as long as we're careful and we go step by step. Now, I want to jump down to example 6, because example 6 is an example that is one that is definitely more complicated after you've separated things into f and g than just sort of your basic derivatives, right? So here, the function we're looking at is sine of x cubed times the natural log of x squared minus x plus 1. So I do see immediately that it is a product rule because I can separate those two functions. If I draw a line down the middle, my f will be sine of x all cubed. My g will be the natural log of x squared minus x plus 1. But when I find each of their respective derivatives, I need to use the chain rule to find the derivative. So I'm bringing back in another process that was a little bit complicated, but that we've been working on recently. So I'm going to have you try this one. Hopefully you are able to apply what you remember from the chain rule. Definitely feel free to look back in your notes if you need to, but I'm going to give you about 3.5 minutes. Try this out, see how much of it you can set up. We're only looking for a first derivative here. Try your best, see what you can figure out, and then we will go through it together. Okay, take about 30 more seconds. All right. So the two functions we're working with are sine of x all cubed and natural log of x squared minus x plus 1. So let's start with sine of x all cubed. This is a parentheses to a power type of chain rule, which is the type we did before spring break. So I'm going to use the shortcut here just for time and efficiency. If you did this with a z substitution, that's totally fine. You should get the same answer. But here I'm going to deal with the power first. So when the 3 comes down, everything inside stays the same, and we subtract 1 from the power. So I get 3 sine of x all squared. And then I have to multiply that by the derivative of the inside. So I look at what's inside, which is sine of x, and I take the derivative of that. The derivative of sine is cosine. So the derivative looks like this. So I'm using a chain rule, right, to find the first derivative. Similarly, we have to do a chain rule on the natural log of x squared minus x plus 1. So this is a chain rule from Tuesday. So the shortcut here is that we take whatever is in the parenthesis and it goes on the bottom. So we have x squared minus x plus 1. And the derivative of that goes on the top. So the derivative of x squared is 2x. The derivative of x is 1. And the derivative of 1 is 0. So there's a complicated sort of situation here where when we find our derivatives, we're using a chain rule or something that is more complicated than just a basic function. Now, we also need to put all of these functions together within the product rule. And so here we also have to be really careful when we're plugging everything in that we don't lose anything along the way. So this one's going to be really long. So let's see if we fit it all here. So we're going to do f prime times g. This is the first part. So f prime, we have 3 sine of x squared times cosine x times g, which is the natural log of x squared minus x plus 1, plus, now we have f times g prime. So f is sine of x cubed times g prime. So times 2x minus 1 over x squared minus x plus 1. Okay, so we have to be careful not to forget any of the terms within the formula. I've definitely been guilty of that. So just be careful that you double check that and that you've gotten all the terms that need to go into this formula to get your final answer. Okay, one other thing I want to point out algebraically, because this is going to start coming up in the homework this week, is that if you have sine of x cubed, which we have here, this is the same thing as if you have sine cubed of x. Okay, these mean the same thing, and so whenever you took pre-calc, you may have seen it written this way, you may have seen it written this way, but I just want to make sure that you know that those mean the same thing. So whether the power is here or out here, these mean the same thing, is that you're cubing the sine x function. Okay. So now we're going to switch gears and we're going to go to the quotient rule. So this is sort of the partner function of the product rule. There were 2 examples from the product rule we didn't do. You can see those on Moodle. If you'd like, you can try them out. But we have to jump over the quotient rule to make sure we have time to cover that as well. So the first thing is, what is a quotient? So product rules, when we multiply 2 things together, quotients are the ratio or when we divide 2 things. So we're looking for functions that are listed as a ratio. So f of x over g of x, that's when you have a quotient. So one function over another one. So here, if we want to take the derivative, of a quotient, there's a really nice geometrical proof of why this formula is true. We don't cover it in this class, but it is in the addendum of the textbook. So if you are interested in stuff like that, you can certainly look it up because it's kind of cool. So the formula here is a little more complicated, right? Because now we're talking about division, and division is more finicky than multiplication, right? So let's talk about multiplication for a second. If you do 2 times 3, that's the same thing as 3 times 2. Right? So it's nice, right? Things don't necessarily need to be super ordered. We still get the same result. Division doesn't work that way, right? So 1 divided by 2 is not the same as 2 divided by 1. So our formula is a lot more strict, I guess, about how we use it. So when you take the derivative of a quotient, the formula looks like this. So f prime of x times g of x minus g prime of x times f of x divided by g of x squared. Okay, so what can and cannot be swapped, right? So like this minus makes it so that these two terms can't be swapped, right? 3 times 2 is not the same thing as, or 3 minus 2 is not the same as 2 minus 3. So we have to make sure that the first term has our f prime of x and our g of x in it, okay? And so it doesn't matter which order. You could do g of x times f prime of x because these two things are multiplied, but these are the two terms that have to come in the first part of it. Similarly, over here, we have g prime of x times f of x. You could do f of x times g prime of x. And the reason why I say you could is if you have already done calculus at some point and you have sort of an alternate way of thinking about this formula, it may be that those are switched. If you've not done this before, then you should just directly rely on the formula and keep things as is. And then on the bottom, we have g of x squared. And so typically we don't square this out, we just write it as g of x squared. Now, from the original function that we were trying to take the derivative of, f of x is always the function on top, g of x is always the function on the bottom. We don't have a choice in how we choose those. The top is f and the bottom is g in order to make this formula work. Okay, so again, we're going to do one pretty thoroughly together, and then, you know, we'll practice other ones. So we're going to do e to the x over x to the fifth. That's the one we're working on here. So we're going to walk through, make sure we understand how this formula works, so that we can see it sort of in action. So once you realize that you're doing a quotient rule, you have one function over another one, we're going to start the setup the same way. So we're going to pick our f and our g, where f is the top function and g is the bottom function. So f is e to the x and g x to the fifth. So you can write it as f and g, you can write it as f of x and g of x. It means the same thing. This is all side work to get to our final answer. The derivative of e to the x, we know from our exponential rules, is e to the x. The derivative of x to the fifth, we have a power rule and we get 5x to the fourth. Okay, so we have all the building blocks. Now we have to plug it into the formula. Okay, so our formula here says we're going to do f prime of x times g. So f prime of x times g, we get e to the x times x to the fifth minus g prime of x times f of x. Okay, so we get 5x to the fourth times e to the x divided by g of x squared. So x to the fifth squared. So as I mentioned, we usually leave this like this. You could write this as x to the 10th, because if you raise a power to a power, you multiply those two powers together. But we don't typically do that. We typically just leave whatever the function is squared. Now, with quotient rules, they can be a little more complicated algebraically because of the division and subtraction. We are less likely to factor this unless we have a good reason to. So we're not going to worry about factoring anything until we get to chapter 4. So this is what, you know, a final answer would probably look like for the quotient rule on like a mini quiz or something like that, or how you could enter it, say, in Wiley. Okay, so that's what the process looks like. I'm going to have you try a sort of basic one, and basic is just sort of a standard one. It doesn't mean it's easy, it just means it's not overly complicated. So we have sine of x over ln x is the one I want you to try. So again, the top function is going to be your f. The bottom function is going to be your G. And then I will write the quotient rule here because you can't see it anymore real quick. Our quotient rule looks like this. The top one, we have the product rule from before, but the quotient rule is down here. So I want you to try this out on this one here. I'm going to give you about 2.5, 3 minutes. Try it out, and then we will go through it together. Okay, take about 30 more seconds. All right. So our f function here has to be the one on the top, so that's sine, and our g function has to be the one on the bottom, so that's the natural log of x. Once we have that set up, we want to find each of their respective derivatives. The derivative of sine is cosine, and the derivative of the natural log of x is 1 over x. Now that we have all our pieces, we just have to very carefully plug it into our quotient rule formula. So we're going to do f prime times g. So we have cosine x times the natural log of x minus g prime times f. So 1 over x times sine x, all divided by g squared. So ln x squared. Okay, so again, there's nothing really that we would simplify here. We would leave the result looking like this. But again, you know, the tricky part is getting things set up and then carefully plugging into the quotient rule formula. So hopefully you got something that resembles this. And then of course, once we are comfortable with the general quotient rule, we start doing some applications and some harder problems. So, dun, 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 we have a tangent line problem here. So we're going to try to find the equation of the tangent line where now our function is a quotient. We have the natural log of x plus 2 over x cubed. So I'll write that a little bit bigger because that's a little small here. And we are trying to find the equation of the tangent line at x equals 1. So again, the original function is ln x plus 2 divided by x cubed. So again, we need a point, we need a slope, and then we need to put it together into the equation of a line. To get the point, we're plugging the 1 into the original function. To get the slope, that's where the quotient rule is going to come in because we need to take a derivative. Okay, so I want you to take about 3 minutes-ish and see if you can sort of apply what we know about this process and use the quotient rule, which is down here, to help you find the slope within this problem. So take about 3 minutes, try it out, and then we will go through it together. Take about 30 more seconds. All right. So again, we're going to need a point and a slope. So let's start by finding the point. We need to plug this one into the original function to find the corresponding y value. So we have the natural log of 1 plus 2 divided by 1 cubed. The natural log of 1 is 0. 0 plus 2 is 2. 2 divided by 1 is 2. So when x equals 1, y equals 2. And we have the point 1, 2 that we're working with here. Okay, so we have a point, and now we need the slope. So this is where our quotient rule is going to come in, because in order to get the slope, we need the derivative. So we're going to go ahead and do our derivative work sort of on the side. So our top function is going to be our f, which is the natural log of x plus 2. And our bottom function will be our g, which is x cubed. We want to find each of their respective derivatives. So here we see a function that has two terms separated by addition. The derivative of the natural log of x is 1 over x, and the derivative of 2 is 0 because that's a constant. The derivative of x cubed will be 3x squared. Okay, so now that we have those pieces, we want to go ahead and put them together to find the derivative of our function using the quotient rule. So our formula says we're going to do f prime times g. So we have 1 over x times x cubed minus g prime times f. So 3x squared. Now, since f has more than one term, I'm going to use parentheses. All divided by g squared. Okay, so you have a choice at this point. You can simplify and then plug in the 1, or you can plug in the 1 as is. It's really a matter of preference. I'm just going to plug the 1 in to see what we get here. So when I plug a 1 into the first term here, I have 1 over 1, which is 1, times 1 cubed, which is another 1. So 1 times 1 is 1, minus, now I have 3 times, now 1 squared is 1, times, and then I'm looking in the parentheses, the natural log of 1 is 0, 0 plus 2 is 2. So I have 3 times 1 times 2 from the second term here. And then on the bottom, I have 1 cubed and then squared, 1 to any power is 1. So that simplifies into 1 minus 6 over 1. 3 times 1 times 2 is 6. So that gives me negative 5. So the slope of my tangent line is going to be negative 5. So now putting that all together, I have y equals negative 5x plus b. So to get my b, this is where I plug in my point. When x is 1, y is 2. So I have 2 equals negative 5 times 1 plus b. So I have to add 5 to both sides, and I get b equals 7. So now that I have all the pieces, I can put them together, and the final equation of my tangent line will be y equals negative 5x plus 7. Okay, that's a 5. I don't know, but like the bottom of the loop got a little goofy. So negative 5x plus 7. So again, the process of finding the equation of the tangent line is always the same, where we're looking at, you know, the point and the slope, but what's changing is the function. And here our function happened to be a quotient, so we had to use the quotient rule. Okay. So we're going to try an example that, again, is going to incorporate in the chain rule. We're going to jump down to example 5 because I want to make sure we're trying some of the harder ones. And so much like when we did the product rule, we want to start out our process using the framework of the quotient rule. And then when we're finding derivatives within that framework, we may have to bring in other rules we know. Okay, so the function that we're looking at here, and I'll write this a little bit bigger. We're going to look at sine of x cubed plus 2x minus 1 divided by e to the 5x cubed. Okay, so we definitely have a quotient. We have something over something else. When we separate these into F and G, what you'll notice is that when you keep the derivatives of each of those, you're going to be putting in a chain rule, right? So we have a chain rule on sine of x cubed plus 2x minus 1, and a chain rule for e to the 5x cubed. So we have to think about what those chain rules are to find our respective derivatives. And then once we have those, we still have to put them all back together within the quotient rule. So there's sort of a lot of steps in this one. This one is definitely on the harder end, but I think we can do it. So we're going to try it. We'll see what happens. I'm going to give you about 4 minutes to try to work it out. Don't worry about simplifying your final answer. Just try to get things done in the form of the quotient rule. Okay, so take about 4 minutes and then we will go through it together. Okay, take about 30 more seconds. All right. So again, we see that we have a function. Our top function is going to be our f, and our bottom function is going to be our g. So we separate those out, and now we need to find each of their respective derivatives. So this is where we see that we're going to have to do a chain rule. Okay, so I know it's a chain rule. I can't split it, right? There's no line I can draw to split this in any meaningful way to make it a product rule or anything like that. So I see that it's a function within a function. So with the chain rule for sines and cosines, I'm going to use the shortcut that we take the derivative of the outside function. So the derivative of sine is cosine. When we do that part, the inside stays the same. But then we have to multiply that by the derivative of the inside. So I look at the inside parts, I see there's multiple terms, so I'm going to use parentheses. And now the derivative of the inside, the derivative of x cubed is 3x squared. The derivative of 2x is 2. Okay. So now over here, when I'm going to do the chain rule of e to the 5x cubed, I remember for exponential functions, I'm going to get the same thing back, e to the 5x cubed, but then I need to multiply that by the derivative of the power. So I look at the power, which is 5x cubed. The derivative of 5x cubed is 15x squared. I'm going to write this in front of the e term. It doesn't matter if it's multiplied in front or after. I just like to have my constants in the front. So now we have all our pieces, okay? And now we're going to put them all together very carefully into the quotient rule. So we have f prime times g. So I start with my f prime term. So I have cosine of x cubed plus 2x minus 1 times 3x squared plus 2. That's my f prime times g. So times e to the 5x cubed minus g prime. So 15x squared e to the 5x cubed times f, which is sine of x cubed plus 2x minus 1, all divided by g squared. So e to the 5x cubed squared. Okay. So this is not trivial, right? Looking at this answer, you can see that this is a very, very complex and complicated function, right? So this is not easy, right? If you're not getting it all on the first shot, that's okay. This is something we have to build up to and work on. We have to be extra careful with the algebra, but again, this requires that you are feeling comfortable with the chain rule because there's a chain rule within the quotient rule. So if you're not quite comfortable with the chain rule yet, then bringing that into another type is going to feel even more complicated. So this is why we need to make sure we're practicing all the different types on their own. And then when we get sort of to the end of chapter 3, which is where we're sort of at now, is when we're sort of starting to bring it all together. So if this felt really overwhelming and complicated for you, then I would encourage you to spend some more time on the chain rule to go back and feel really comfortable with that, and then come back to the quotient rule that uses the chain rule within it. Okay, so I don't think we're going to have enough time to do example 4. That one takes quite a bit. So we'll stop here. Example 4 is on Moodle. You know, I'll show you the reason why it takes so long. The first derivative of this is not terrible, but the second derivative is pretty long. So I would say try it out and then see if you can, you know, get to the right answer and then check it once you've done it. The second derivative, I'll just show you. Looks like this. So it's really, really long and complicated. The first derivative of the quotient rule is not terrible. It's like what we've been doing, but the second derivative is really long and it's on the harder end of things. We don't typically do a lot of those, but it's worth trying it once just to make sure you can get the structure down. Okay, and again, that is on the videos on Moodle, so you can check the answer there. Otherwise, I hope you have a great rest of your day. Don't forget about the quiz on Monday, and there is a review tonight if you think that will be helpful. All right, have a good rest of your day.